All right, you guys ready? Okay, so today we are going to be doing 5.2a, which is definite integrals. So the introduction of, because we're only really introducing it today. So you all know what a Riemann sum is, because that was vocabulary on your last quiz, of course. And you all know what you don't all know what a definite integral is. So a definite integral is an integral evaluated at the upper limit minus the integral evaluated at the lower limit, resulting in the total net area under the curve. Okay, total. So here's what you need to know about how these two things are associated with each other. With a Riemann sum, okay, and these vocabulary words, you know I like to throw these on tests and quizzes, so you know nothing is safe in here, okay? If it's on your notes, it might be on the test, it might be on a quiz, so make sure you're paying attention to that. So, number of rectangles, okay? You know if we do a Riemann sum, we sometimes have like 4, sometimes we have 5, sometimes we have 3 rectangles. What if we used infinitely many rectangles? That would give us what? The perfect exact area under the curve, correct? So what we're going to be doing with the definite integral, essentially we are doing that mathematically, okay? Now we don't actually sit there and do that, but what we're doing mathematically amounts to that, all right? So, definite integral. Now this right here is the limit conversion definition. That's part of 5.3, but I've decided writing limits is challenging and difficult, and I don't want to waste a ton of time on it at the end of the year because there's other important things I want to address with you all. So we are not going to write limits, but you do have to know that you can always rewrite an integral as a limit. Okay, that's the extent of what I want you to know, all right? So this part, of course, you do have to know. You do have to know what integral notation looks like. It's going to be this S-looking symbol, okay? S represents the sum. You're basically adding a bunch of things together, okay? From upper limit to lower limit, a to b, of the function, and then d of x, dx is what we call a dummy variable. It's called Leibniz notation, I believe that's how you say it. But that is something we can learn more about. They learn more about it in AP, BC, and all that. We're not going to talk as much about the notation. I just want you to be able to understand it. So the main idea here you need to understand is dx is telling you you're going to be taking an antiderivative, okay? So when you see that dx, you're going to take the antiderivative. Once you take that antiderivative, no more dx and no more s symbol, okay? Now, you know when you take an antiderivative, in general, you put plus c at the end? You do not have to do that for a definite integral. Okay, you only have to do that when we don't know what the boundaries are. Does everybody understand what I'm saying by that? All right, perfect. Let's go ahead and try one together. So, we're going to sketch the areas. We're going to take the definite integral, and then we're going to compare it to one of the Riemann sums. All right? So step 1, if I want to graph this, you could choose to make a table, right? Plug some values in. What would be an easy number to plug into this function right here? 1. What's the square root of 1? 1. Now, you're always going to at least need to plug in the boundaries, right? So I'm going to have to plug in the 0. What's the square root of 0? So we got a 0.00. And if you plug in 2 and 3, you're going to get numbers that are not very nice, right? Decimal. What if I plug in 4? 2. So this right here is our entire function on that interval. So everybody see how I got that? Okay. Now, we don't have to graph the whole thing, and nor can you even go to the left because this is a root. You can't take the square root of a negative. So what you're essentially doing when you take the antiderivative on this boundary is you're finding the area between the x-axis and the function. Okay, so this is the area you're going to be finding, the area between the x-axis and the function. Okay, so here's how we do it mathematically. You're going to make your big integral symbol, your lower boundary, your upper boundary. Now, you can rewrite this function as what? What's another way to write this function? Good. So you could have done it now or later, but I just find it easier to write it as a fraction because I know I'm going to have to take the antiderivative, and I know it's going to be easier if I have it as a exponential fraction instead. You know what I'm saying?
I feel you.
Okay, perfect. So this would be the definite integral. This would give me the exact area under the curve from 0 to 4. Okay, so we're going to actually evaluate this. So the way we evaluate this is once you take the antiderivative, you no longer are going to put the dx or that s symbol here, okay? Because that indicates that you haven't done it yet. So you're going to put these little boxes, okay? How would we take the antiderivative of this? What do we do with the exponent?
Increase it by 1 and divide it by the constant
Good.
variable.
Increase it by 1 and divide by the new exponent, right? What's going to happen when I divide by 3 halves?
It's gonna be 1 over 2 halves.
No, it's going to be just 2 over 3.
2/3. Yep, so it's the reciprocal. Of course, you could do 1 divided by 3 halves, keep, change, flip, and it's going to give you that as well. So this would be the antiderivative. Like I said, on a definite integral, you do not have to put plus c because you already know the boundary of that function that we're using it on. You're going to put the limit out here, okay, where you're going from. Now here's how you actually evaluate it. You're going to take the upper limit and you're going to plug it into the function. You're going to then take the lower limit and you're going to plug it into the function. And between them, you're always going to subtract upper limit plugged in minus lower limit plugged in. Does everybody see what we did there? Okay. So mathematically, 4 to the 3 halves is the same thing as the square root of 4 to the third. 4 to the third is 64. The square root of 64 is 8. 8 times 2 is?
16.
Yep, good. So that's 16 over 3. Now, what's going to happen with this whole thing over here? 0. So it's just 16 over 3, which is approximately 5.3. Yeah, 5.3 approximately. Now, the reason I wrote it as a decimal approximation is because I want to make sure that you are going to recognize about what that area is. So, if you think about it for a second, we could do a Riemann sum approximation and see how close we get to the actual answer to kind of compare what we learned about last week. So, do you guys want to do LRAM or RRAM? Or would you rather do trapezoidal?
What's the hardest one?
Trapezoidal, you want?
What's the easiest one?
LRAM and RRAM are the same easiestness, right? Easiestness?
Yeah.
Okay, we'll do LRAM. Why not? So LRAM is going to be based on the height of the left side of each interval. Now for this particular situation, I didn't give you the amount of rectangles, so you're going to get to pick. So I would just say let's just go 0, 1, 2, 3, 4, each one with a width of 1. That's going to be the easiest option, right? So this one is going to be 0. This one's going to have a height of 1. This is going to have a height of, well, we don't know mathematically, we'll figure it out, and then a height of square root of 3. So keep in mind, this height is 0, this height is 1, this height is radical 2, right? And this height is radical 3. Because it's the square root of, I'm plugging that x value into the function to get what that height is. Does everybody see how I got that? Now, why do we not care about this height right here? The last, because I'm using LRAM, the last one's never going to come into play, right? So the width, as we said, is 1. So it's going to be 1 times 0 plus 1 plus, plus the square root of 2 plus the square root of 3, right? We're going to do that mathematically. And we should get 4.15. Now, just for fun, this is LRAM, right? The only thing I would have to change in this to make it RRAM is to do plus 2 instead of plus 0, correct?
Yes.
So just because, I'm going to try it out and see what I get. Just so we can have more of a discussion about this. So I just did RRAM really quickly, and for RRAM I got 6.15, okay? I meant to write RRAM there, sorry. So does everybody see how I got those using just RRAM and LRAM methods?
Yes.
Okay. So what do you notice about, this is the actual exact area. What do you notice about that value? It's in between because, do you notice what this function is doing? Is it increasing or decreasing?
It's increasing.
It's increasing. When a function's increasing, LRAM is an under approximation. When the function is increasing, RRAM is a, and our value must fall somewhere in the middle. If we did, for example, trapezoidal, I'll just talk about what would happen. This function, would you say it's concave up or concave down? It's concave down. Concave down, it would be an under approximation, but it would be more precise than LRAM. So it would be somewhere between 4.15 and the actual answer. Okay, you see how this is all coming together now, hopefully. All right, perfect. So for the next one, we're doing cosine stuff. So step one is we got to graph this. Now, when we're graphing something with cosine, we're not going to go like putting in 1s, 2s, 3s, right? We got to put in degrees or radians. So I'm going to actually graph this, but I'm going to go like by 45s, but I'm going to skip one just so because I have room and I might as well use it. So I'm going to go here at negative pi over 4. Here I'm going to go negative pi over 2. So I'm going by 45s, but I'm just skipping a line. Technically I'm going by 22.5s if you want to be precise here, because I'm just trying to skip a line to stretch it out so it's not so crammed. Okay, this would be pi over 4, and this would be pi over 2. Does everybody see what I did there? I just did it so I can graph it. Now, in order to graph it, I'm going to have to plug these values into the function. So what's cosine of negative 90? Same thing as pi over 2.
Oh, 1?
1, good. Or no, not 1.
0.
0.
Sorry, I always get sine.
Me
and
too,
cosine
I do the
mixed
same
up.
thing.
Yeah.
That's why I said
Yeah.
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 Yeah, because cosine is like the upside down bowl shape, and sine starts at 0, so it's always 0, 0. So then regular 90 is also 0. Cosine of 0 is 1. Now instead of just going, I'm going to go by 0.5s, because now I don't have to like cram my graph down. It's going to be right here. Okay. If you even wanted to, you could go by 0.25 and make it a little higher. So whatever you think is easier. So it's at 1. And then does anyone remember what cosine of 45 degrees is? Radical something over something.
Radical 3 over 2. Radical 2 over 2.
Radical 2 over 2, which is approximately 0.7. So we're about here. So the graph, it's gonna be hard to draw how it exactly looks, but it does kind of curve out. It's not like has semicircle, okay? It's like that. 'Cause we're looking at a very small portion of the sine and cosine graph, right? Or the cosine graph. So any questions about how we got that? Just graph sketch. Now remember, we're always finding the area under the curve, the area that exists between the curve and the
X-axis?
the x-axis. Okay, that's like a vocabulary question I might ask you. Okay, the area between the curve and the x-axis is always what you're finding when you do a definite integral. So now we're going to write our definite integral. What's going to go down here? Negative pi over 2, and what's going to go up here? Good. My function's going to go here, cosine of t. Now here's where you have to be careful. Is this one going to have a dx in it? The dx has to be the same variable as the function has. If I differentiate this, or if I dt. So do you remember when you learned about implicit differentiation? Same idea works in the reverse. If you were to integrate this in terms of x, it would be cosine of t times x. Okay? So you have to set the variable as what you want it to be that you're integrating in terms of. Does that make sense?
Yeah.
Okay. So does anybody remember what the antiderivative of cosine is?
Sine.
Sine. And I'm going to evaluate that from what values?
Pi over 2 and negative pi over 2.
Good. Pi over 2 to negative pi over 2. So sine of pi over 2 minus sine of negative pi over 2, right? Sine of pi over 2 is the same thing as sine of 90. What is sine of 90?
Oh, fuck.
Well, cosine of 90 is 0, so,
So 1.
so 1. So sine of negative 90 is negative 1, right?
Oh, so it's going to be 2.
So it's going to be 2. Which makes sense. Now keep in mind, we scaled our graph, so I know it looks like there's like 8 boxes in here, but we scaled it so it's not quite like that. So now this is exactly 2. So that area is exactly 2 under the curve. So we can use estimation to verify if this is close or not. So let's say we use LRAM on this particular scenario. This height of this rectangle from here to here is going to be 0. This height is going to be radical 2 over 2, right? This height is going to be 1. And this height here is going to be whatever this one is. So here's what's weird.
It's overestimated and underestimated.
at the same time, right? The left side is under and the other side is,
Over.
which makes sense because we use LRAM. When the function is increasing, which is doing from negative pi over 2 to 0, it's an under. But when it's decreasing, we know it's an over, which it is doing from 0 on to pi over 2.
Mm-hmm.
So does that make sense why it's both over and under in this case?
Yes.
Okay. So now we're going to actually find that area. Now the width of this is actually pi over 4, 45 degrees, over, or times 0 plus, remember this is radical 2 over 2, plus 1 plus radical 2 over 2, height again. And that would be all my heights. So if you do all this calculation stuff, just be regular radical 2 plus 1 plus 0 times pi divided by 4, I get the answer of 1.9. Is that close to our answer?
That's very close.
Very, very close, right? And I want to mention why this one is closer than the last. So with the last we did right, we did left. What's weird is what would happen if we did right was it would be, I'll just draw it in for you guys real quick. Right would be here,
You did the exact same thing.
But it's opposite.
but in different spots, yeah.
Yeah.
So keep in mind, the right and the left in this case would end up being the same thing, just flipped around. So right approximation would give you the same mathematical answer, okay? So keep in mind when it's like this, when the graph is symmetric over the x-axis, for this particular case, LRAM and RRAM are going to be
Oh.
the same, right? Does everybody see that? All right, so I'm just trying to help you understand the reasoning behind everything you learned in the last chapter, okay? Because you know, with me, the reasoning is really big. I'm always about the reason behind things versus just why. Yes?
Can you ever calculate the area of a curve if it's underneath the x-axis? So,
Yes.
oh no.
So all that means is any of the areas that are underneath is counted as negative.
Okay, gotcha.
Yep. So, like, for example, we're going to get into that, trust me, but, like, if two pieces, if it's, like, the same amount under and the same amount over, it's 0.
Okay, that's cool. Okay,
Yeah.
okay.
All right, I'm going to hand out the homework.